In this video, we're going to look at solving logarithmic equations. So if you watched the last video, we were solving exponential equations using logarithms. To solve a logarithmic equation, we're going to convert to exponential form. Now, one of the things you have to be mindful of with logarithmic equations is that we do need to check for extraneous solutions. The reason we have to check for extraneous solutions is because our logarithms have a restricted domain. We can't take the log of a negative number, or we can only take the log, let me rephrase, of a positive number. So our arguments have to be strictly greater than 0. We can't even take the logarithm of 0. So what we'll be doing is we'll be checking that the solutions we have that we end up with from our exponential equations still work in that logarithmic form from the original problem. 4 times the natural log of x equals 36. We want to start by getting the logarithm by itself. So I want to get rid of that 4. I'm going to divide both sides by 4. I have the natural log of x equals 36 divided by 4 is 9. Now we want to remember that the base of a natural logarithm is e. And now we're just going to convert to exponential form. So take that base, raise it to what it's equal to, set it equal to the argument. We have e to the 9th power equals x, and we're done. There's our solution for x. But we need to check that. So our only argument is x. So if I plug in e to the 9th, is that going to be positive? And yes, it is. So e to the 9th is our solution. As an approximate answer, this is 8,103.08, approximately. Again, e to the 9th is our exact form. 8,103.08 is an approximation. So a lot of times we'll ask for both versions or both forms of that answer. Log base 3 of x cubed minus 5 equals 1. We're going to go ahead and convert to exponential form. So 3 to the first power, or just 3, equals x cubed minus 5. We'll go ahead and isolate that x term. So we're going to add 5 to both sides. So we get x cubed equals 8. And then we want to take the cube root of both sides. With a cube root, we do not add plus or minus. We only add plus or minus if our index is even. So x is equal to, the cube root of 8 is 2. And then we're going to check that 2 cubed minus 5 is positive. So 8 minus 5 is positive. That solution works. Log of 2x plus 1 plus log of x equals log of x plus 8. To solve an equation like this, we need to begin by condensing on the left-hand side so that we only have one logarithm on the left. So this is going to condense using multiplication. This is log of x times 2x plus 1 equals log of x plus 8. And now we can apply the 1-to-1 rule. If I've got log of something equals log of a different thing, those two things that we're taking the log of have to be the same. So x times 2x plus 1 must equal x plus 8. 2x squared plus x equals x plus 8. I'm going to subtract x from both sides, so they end up going away. Summing to 0, we have 2x squared equals 8. X squared equals 4, dividing both sides by 2. And then when we take the square root of x squared, we need to make sure we add the plus or minus on the right-hand side. So x is equal to plus or minus 2. When we go to check our solutions, we want to make sure we use that very original problem. We don't want to use anything that we've condensed. Go back to that original problem that was provided. We're going to check both of our solutions in every single argument. So first with positive 2 is 2 times 2 plus 1 positive? Is 2 positive? Is 2 plus 8 positive? So all I'm doing is plugging in my solution into those arguments. 2 times 2 plus 1 is positive, 2 is positive, 2 plus 8 is positive. So x equals 2 is a solution. X equals -2. I already can tell it's not going to work because 2 times -2 plus 1, well, that's not positive. -2 is not positive. Even though -2 plus 8 is positive, since it didn't work in the other two arguments, it's not included. It's an extraneous solution. Log base 3 of 4x plus 1 times x plus 1 equals 3. We'll convert to exponential form. We have 3 cubed equals 4x plus 1 times x plus 1. 3 cubed is 27. And now we're going to FOIL on the right-hand side. We FOIL on the right-hand side, we get 4x squared plus 4x plus 1x is plus 5x plus 1. Now we want to set this equal to 0, so we're going to subtract 27 from both sides. So 0 equals 4x squared plus 5x minus 26. I'm not going to try factoring this. I just think that there's going to be a few too many combinations for me, so I'm going to use the AC method. I need factors of a times c, or 4 times -26, which is -104, that sum to 5. This is the only part of the AC method that requires trial and error. So start taking that 104 and dividing it by numbers. You end up getting 8 and 13. So I just work with positive 104 and just try to find numbers that might give me 5. And I'll worry about the signs later. So I started dividing 104 by 4, 104, I didn't try it by 5, by 6, by 7. Eventually I got to 8. So 8 and 13 are factors of 104. Since the product is negative, one of those two values needs to be negative. Since I want them to combine to give me a positive 5, I'm going to make that 8 the negative value. Now I'm back to my work on the left, and all I'm going to do now is split up that 5x term using those two factors we just found. So 4x squared minus 8x plus 13x minus 26 equals 0, and I'm going to factor by grouping. 4x squared minus 8x, I can factor out of 4x, and I'm left with x minus 2. 13x minus 26, I can factor out a positive 13. I'm left with x minus 2. The like factor of x minus 2 tells me I'm on the right track. My first factor is x minus 2. My second factor is 4x plus 13. Now, you might have gotten there using trial and error, and that's fine. The magnitude of 26 and 4 just made it so that I wasn't willing to try the trial and error. So setting each of these factors equal to 0, we get that x is equal to 2, and x is equal to negative 13 over 4. Now, when we check, we only actually have one argument. It's that big product. You can choose to use the factored form or the expanded form. I'm going to use the factored form, though. So I've got 4 times 2 plus 1 times 4 plus 1. Well, this is a positive times a positive, which is going to be positive. So that first value of x equals 2 works. X equals negative 13 over 4. I've got 4 times negative 13 over 4 plus 1. Negative 13 over 4 plus 1. 4 times negative 13 over 4, this is actually just negative 13 plus 1. And then negative 13 plus 1, negative 13 over 4 plus 1. This is negative. I'm just going to keep that negative. I can see that this is a negative times a negative, which is positive. So both of those solutions we found check out. Log base 2 of 2x minus 5 plus log base 2 of x minus 3 equals 3. We're going to start by condensing on the left-hand side. We've got log base 2 of 2x minus 5 times x minus 3 equals 3. And now that we have one logarithm on the left, we can convert to exponential form. 2 to the power of 3 equals 2x minus 5 times x minus 3. 2 cubed is 8. We're going to FOIL out on the right. 2x times x is 2x squared. Minus 6x minus 5x is minus 11x. Negative 5 times negative 3 is positive 15. Set this equal to 0. 2x squared minus 11x plus 7. Looking at this, factors of, just thinking about the AC method, we've got 2 times 7 is 14. We're not going to be able to find factors of 14 that add up to negative 11. So quickly I can identify this is not going to factor. I'm going to have to use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So 11 plus or minus the square root of negative 11 squared minus 4 times 2 times 7, all divided by 2 times 2. Negative 11 squared minus 4 times 2 times 7, that's going to simplify to 65 over 4. I'm going to use some decimal approximations here for this. That's going to make checking much easier. My positive solution, so 11 plus the square root of 65 divided by 4 is about 4.77. 11 minus the square root of 65 divided by 4 is about 0.73. So I'm going to first check that solution of 4.77. Remember, I'm going to use that original equation. So I've got 2 separate arguments I have to check. I'm not going to look at the product of the 2. So we've got 2 times 4.77 minus 5. I need to verify that that's greater than 0. 2 times 4.77, it's going to be more than 8, so that's going to be positive. I also need to check that 4.77 minus 3 is positive, and both of those are positive. So I know that the solution 4.77 works. We'll check the next solution, x equals 0.73. 2 times 0.73 minus 5. Greater than 0. I don't think that's going to be greater than 0. 0.73 is pretty close to 0.75, and 2 times 0.75 is 1.5. So that's not going to be positive. Since that first argument's not positive, I don't even need to check the second one, but we can for good measure. 0.73 minus 3 greater than 0. That's also not going to work. So x equals 0.73 is an extraneous solution. It's not a solution for our equation. The natural log of e to the natural log of x minus the natural log of x minus 4 equals the natural log of 5. The first thing we're going to do is work with this natural log of e to the natural log of x. There's a couple of ways we can look at this. It might be the easiest just to convert or to use the power rule to bring down that natural log of x exponent. So that would be the natural log of x times the natural log of e minus the natural log of x minus 4 equals the natural log of 5. Remember that the natural log of e is 1, so this first term is simply the natural log of x. We can condense on the left using the quotient rule. So we have the natural log of x over x minus 4 is equal to the natural log of 5. And now we can apply the 1-to-1 rule that says that natural log of a equals natural log of b, then a must equal b. So in this case, the natural log of x over x minus 4 being equal to the natural log of 5 tells me that x over x minus 4 equals 5. I'm going to multiply both sides of the equation by x minus 4. So we have x is equal to 5 times x minus 4. Distributing the 5, x is equal to 5x minus 20. Subtracting 5x from both sides, we have negative 4x equals negative 20. And dividing both sides by negative 4, we get x is equal to 5. Check, we've got two arguments. We've got e to the natural log of 5. That's greater than 0, and 5 minus 4 greater than 0. Both of those check out, so our solution is x equals 5. All right, our last example before we get into an application problem is the natural log of 2x minus 5 plus the natural log of, log base 2 of 2x minus 5 plus log base 4 of x minus 3 equals 3. Notice the different bases here. We can't do a whole lot when we've got different bases, so we're going to apply the change of base rule. I'm going to use just a logarithm, a common log, so log of 2x minus 5 divided by log of 2 plus log of x minus 3 divided by log of 4 equals 3. Now, when I think about solving a rational equation like this, I want to multiply through by the LCD. So I kind of want to figure out how to make these denominators, log of 2 and log of 4, look the same. Log of 4 is equal to log of 2 squared, or 2 log of 2. So I can see that the denominator of my first fraction is log of 2. The denominator of my second fraction is 2 log of 2. My LCD is 2 log of 2. So I'm going to multiply each of my terms in my equation by that LCD. When you distribute that LCD to each term, we can start simplifying. In the first term, log of 2 over log of 2 is 1. In our second term, 2 log of 2 divided by 2 log of 2 is 1. And in my third term, nothing's going to simplify out, but we are going to simplify it here in the next step. So in the first term, we're left with 2 log of 2x minus 5 plus log of x minus 3 from the second term equals 6 log of 2. Let's apply the power rule. So this is, and we're going to apply the power rule and condense on the the left-hand side. So we've got log of 2x minus 5 squared times x minus 3 equals log of 2 to the 6th power. So we're using that power rule on the right-hand side as well. Applying the one-to-one rule, the argument of the log on the left must equal the argument of the log on the right. So 2x minus 5 squared times x minus 3 equals 2 to the 6th is 64. Now we can FOIL out the 2x minus 5 squared and then multiply that by the x minus 3. We're going to end up with a cubic. It's going to be something that we're not going to be able to solve. So we're going to go ahead and just set this equal to 0 without expanding and use our calculator. So 2x minus 5 squared times x minus 3 minus 64. We're going to figure out where this equals 0. All right, so in Desmos, we're going to type in the left-hand side. So we've got 2x minus 5 squared times x minus 3 minus 64. And if I zoom out a little bit, just seeing if there's any other zeros, we can see the 1, but maybe we want them, just double check. It didn't look like there was any others. So that 0 is when x equals 5.198. So there's our solution. Sometimes we're going to have to use technology to find those solutions. All right, but now we have our solution. We need to check that it works with the given problem. So we're going to plug it into the two original arguments. 2 times 5.198 minus 5. We want to verify that that's positive. And 5.198 minus 3 is positive. 2 times 5.198, that's going to be more than 10. Minus 5 is still positive. And 5 minus 3 is positive, so our solution checks out. All right, and our last problem for the video is a nice application problem. That we're using Newton's law of cooling. So the equation T of T equals A times E to the KT plus T sub S can be used to determine the temperature of an object T after some amount of time. A is the difference between the initial temperature of the object and the surrounding air. K is a constant. It's our continuous rate of cooling, so this is going to be different depending on the scenario. And T sub S is the temperature of the surrounding air. A pot of boiling soup with an internal temperature of 100 degrees Fahrenheit was taken off the stove to cool in a 69-degree Fahrenheit room. After 15 minutes, the internal temperature of the soup was 95 degrees. Use Newton's law of cooling to answer the following. Write a formula that models the situation. So we're going to use that model that we have above. T is equal to, A is that difference between the initial temperature of the object and the surrounding air. So the initial temperature of the object or of the soup was 100 degrees. The air was 69 degrees, so that difference is 31 degrees. Now we aren't given a value of K, and T is our variable. So we're going to leave that E to the KT plus the temperature of the surrounding air was 69. Now to finish setting up this formula, we need to solve for K. We're going to solve for k using the fact that they told us that after 15 minutes, so when when time was 15 minutes, the little t is 15 minutes, the temperature of the soup was 95 degrees. So we're going to plug those values in for big T and little t. We get that 95 is equal to 31 times e to the k times 15 plus 69. And now we have an equation with just one variable k, which we can solve for k and finish that model. We'll subtract 69 from both sides. And that's, I'm sorry, I was trying to find where in my work we were at, which is 26. So 26 is equal to 31 e to the 15 times k. We'll divide both sides by 31. I'm going to leave that just as a fraction. The next step, to isolate that exponent, we want to take the natural log of both sides. So the natural log of 26 over 31 is equal to the natural log of e to the 15k. And that inverse property tells me that the natural log of e to the 15k is just 15k. So the natural log of 26 over 31 equals 15k. To find k, we're going to divide both sides by 15. So the natural log of 26 divided by 31 divided by 15 equals k. And using a calculator, we're going to approximate this to be about negative 0.0117. So this tells me my model T of t is equal to 31 e to the negative 0.0117 t plus 69. So the temperature of an object is equal to 31 times e to the negative 0.117 times the amount of minutes plus 69. To the nearest minute, how long will it take for the soup to cool to 80 degrees Fahrenheit? So now we know the final temperature is 80, and that equals 31 e to the negative 0.0117 t plus 69. We're going to solve this equation for t the same way we solved the previous equation for k. We're going to start by subtracting 69 from both sides. We get 11 equals 31 e to the negative 0.0117 t. Divide both sides by 31. So 11 over 31 is equal to e to the negative 0.0117 t. Take the natural log of both sides. So the natural log of 11 over 31. When I take the natural log of the right-hand side, this just leaves me with negative 0.0117 t. And then to get t by itself, we're going to divide both sides by negative 0.0117. We get 88.55. It wanted us to round to the nearest minute, so we're going to say 89 minutes. It's a really long time. That soup has taken a long time to cool down. To the nearest degree, what will the temperature be of the soup after 2.5 hours? So if we're looking at 2.5 hours, then that means our time is 2 times 60 plus 30, because our time was measured in minutes initially. So this is 150 minutes. So the temperature of 150, or the temperature at 150 minutes is equal to 31 times e to the negative 0.0117 times 150 plus 69. We're going to type this into our calculator. We get 74.36. So we're going to, rounding to the nearest degree, say that the temperature after 150 minutes or 2.5 hours is about 74 degrees.